Very pleasant morning to all. I would like to extend a warm welcome to everyone. Thank you for joining us for today's webinar. My name is Ms. U. Srinidhi, Assistant Professor, Department of Mathematics PG, K.S. Rangasamy College of Arts and Science, Autonomous, Tiruchengood. Today we are presenting National Webinar on Applications of Graph Theory, presented by Dr.G. THAMIZHENDHI. Just a little instruction before we get started. If you have any questions during the presentation, please type them into the chat box. I will bring them up during the presentation, and we will also have time for the questions at the end. Now I request our HOD, Ms. M. Sujata, to welcome the gathering.
A very good morning to all. On behalf of K.S. Rangasamy College of Arts and Science, I welcome you all to this national webinar on applications of graph theory. First and foremost, I would like to express my sincere thanks to our Honorable Chairman, Line Dr. K.S. Rangasamy MJF, Vice Chairman Mr. R. Srinivasan, Executive Directors Mrs. Kavita Srinivasan for their support and permission to conduct this webinar. My hearty welcome to our beloved principal, Dr. V. Radhakrishnan, in his absentia. It's a glorious moment to extend my warm welcome to our today's resource person, incredible researcher, Dr.G.THAMIZHENDHI, Assistant Professor of Maths, Sri Vasavi College, Erode. Welcome you, ma'am. On behalf of my institution, I cordially invite all the participants from various destinations. I also extend my genial welcome to my colleagues and my dear students community. Once again, I welcome you all. I ensure this national webinar will provide a platform for enriching your knowledge in graph theory, and next few hours will be enjoyable and fruitful for every one of you. Thank you.
Thank you, ma'am. Now I call upon Ms. C. Sindhuja, Assistant Professor, to introduce our speaker.
Good morning to all. Dr. G. Tamizhendhi is currently working as an assistant professor in PG and Research Department of Mathematics, Sri Vasavi College, Erode. She has completed MSc, MPhil and obtained PhD in Bardar University. Prior to joining in Sri Vasavi College, she was worked at Vellala College for Women as an associate professor and head from 2004 to 2019. She has 16 years of experience in teaching. She has produced 14 MPhil research scholars. 3 PhD research scholars are currently pursuing under her guidance. She obtained funding from UGC for undertaking research on intuitionistic fuzzy graph. She has presented 27 research papers in the conference and published 15 research articles in the international journals. She has organized more than 50 programs, including FDPs, workshops, and conferences in the area of mathematics for research scholars and students. She delivered 25 invited talks in various colleges. Dr. G. Tamizhendhi was served in different committees in Vellala College for Women. She also acted as a chairman, PG Board of Studies in Vellala College for Women, and member Board of Studies in Erode Arts and Science College and Gobi Arts and Science College. She has received Best Faculty Award from NFED, Negru Group of Institutions and Vivekananda Institutions. She also received a Best Researcher Award from Intelligent Research Foundation, Chennai. She has received a gold medal for the NPTEL online certificate course on advanced graph theory. Thank you.
Thank you, ma'am. Next, I hand over the session to our resource person.
Good morning, participants. I thank the organizer and head of the department, to giving me the opportunity to present applications of graph theory. Now I am sharing my screen. Are you able to see my screen? Anyone please? Are you able to see my screen?
Yes, ma'am.
Okay, good. Today we are going to see what are the applications of graph theory. My presentation outline is first going to concentrate on what are the graph and block models and what are the some important graph terminologies and also special types of graphs and how to represent this matrix representation and graph isomorphism and applications of graphs. First, before going to graph models, first we know the what is we have the two types of data involving in real life problems. One is discrete data and continuous data. But is we have the discrete mathematics. The graph theory deals with the discrete mathematics. Therefore, we can concentrate on discrete. What is discrete maths? We have the data in discrete in name itself. We have the name that is discrete in nature. That is, we have to represent the data in discrete. Therefore, we can have the discrete mathematical structure. And we represent this discrete mathematical structure is by the integers concept. We all know the integers. It is in the discrete integers. And what are the continuous objects? Continuous objects we can have this. We have represents in real numbers. Okay, now we go for in graph theory model. We go for discrete data structures. Now here are some of the examples. Now, what is the data? The number of students in a class we have left in half an hour. Therefore, it may be in discrete nature. And there is the results of rolling two dice. It may be in the values 2, 3, 4, 6, 7, 8, and 10, and 11. It may be the result for the data. Therefore, this type of situations we can represent in discrete data. What is some of the examples I given for discrete and what are the continuous data? Here, discrete data can take the only certain individual values, and its continuous data can take in the continuous and range of the values. Here, for example, suppose you want to count the number of pages in a book, it is in discrete variable. Suppose you are to the shoe size. The size of the shoe, it is we have involving in discrete data. That is, it is not in the range. It may be 5, 5.2, 6, and 6.2 in size. Therefore, it is in discrete and range. Number of people in a race is also is represents in discrete variable. But here, suppose you want to find the length of the film, it is in continuous in nature. Suppose you want to calculate the temperature of your human body, it may be in continuous nature. Therefore, time taken to run a race, it is a continuous nature. Therefore, we going to deal with the discrete nature of the types. Here some of the examples are given. We can guess which one is belongs to discrete and are continuous. Suppose volume of your cell box and shirt collar size, number of goals in a season, and speed of your car, population of your town, length of your crocodile, number of pages in your number of box. This is the which one is belongs to the discrete and continuous. Can you guess this one? You can guess which one is belongs to discrete and continuous. Here, this is the answer. We can classify this one is a continuous and this one is a discrete. We can classify population of your town, number of pages in your box. It is not in continuous nature, therefore the data in discrete. Shirt of collar size and number of goals in a season. These are the continuous data. Suppose we are coming to college on time 10 o'clock. some students are come to 10 and some students are come other intervals 10 5 this one. Therefore, this type of situations can be represented discrete models. This discrete model structure can be modeled in graph model. Here, what is first? I'm going to tell what is a graph. Something is mined in like look like here data. Data means graph means this type of this is in number line. This other pie chart. This type of graph comes into your mind, but it is a graph. But we can have in graph theory we can see the relation between the objects. This is a sine graph, but it is not a graph. Graph first, before going to the basic definitions of graphs, I'm going to why the graph model is arise. Here, the graph model is arise based on this coding bridge problem. Here already already most of them are familiar are here about this coding bridge problem. Here, this is the famous problem. This is the origin of graph theory. For here we are doing lot of research and have a lot of applications in graph theory model, but this is the problem, is the base problem. Here what is the problem here? Here there is a one city is Boring Bridge. It is situated in Bengal River, and also this city is occupied by two islands. And this city, this occupied by two islands. These two islands can be traveled by 7 bridges. Okay, this is the problem, and this in this the people want to travel all the places by using this bridges without any repeating the edges. This is a problem. Okay, but this problem is arised in 1736, 17th century. Here, this is a city, and this the red line is marked as red line is indicated as the 7 bridges, and here the two islands. Okay. Here, this already I told. Here, the residents want to travel all the areas without repeating the edges using the 7 bridges. Here, can we have find any way to travel this all the cities by using the 7 bridges? They posted one problem in this one. Therefore, in 1736, Euler has, this is the person introduced this graph theory concept. Here, Euler is arranged, which is 1707 to 1783, and here he solved this solution. Solve this problem. It has no solution. We give the solution for this problem, and he is the person have in 1738 he have his right eye is blind, and 1766 is total two eyes are blind. After this blind, he is doing research. Even his aunt is later going to blind. Even though he is blind, he keep on doing a research. He contributed many results for mathematics. Here turn this problem. Here he have give solution for this one. He reformulating this problem into graph model. This is the base. Here how to he reformulate this model? Here this four land areas, already I told, this four land areas, this four land areas he represent as a vertices or nodes and some other term we have used for represent this land areas. Here the dot line, here A, B, C, D is the four land areas, and here the lines may be easiest as a edges. Here the 7 bridges. The 7 bridges is named as a edges. Here the line indicated as a line from A to B. We have A to B. We have two lines, and B to D. There is edges. We have the edges are lines we can represent connecting between two land areas, and B and C. Therefore, this is the 7 bridges. In this real life problem, he formulated as a graph model. This is the base for our graphing. Okay. And here anyone can guess how to travel this four land area by using the seven bridges without exactly once. We can start anywhere. Here we can start A and going to B. We can start A to E. Therefore, this is not possible to travel all the seven bridges and for the cities using the seven bridges without any repeating the bridges. Okay, he gave this solution. Okay, Euler found out the solution. Here, what is here he posted here is there is no solution. There is no solution for this problem. Okay. Here, but still, someone is told there is a long-standing problem, but he told that there is no problem for this solution. Okay. Why he has a no solution for this problem? Because in this graph, here we have the all the suppose you want to travel one place to another place without repeating an edges, we need this the degree of this the nodes must be even, but here the degree of the nodes is odd, where therefore it is not possible to travel all the areas without repeating the edges. Okay, therefore he find the solution for this problem. Okay. Therefore, this is the problem, impossible problems. This is the beginning of this node. Okay. Suppose we have to. This is also still long-standing problem. No, anyone who have to find out the solution for this one, you can pose this problem. So I am given some of the books for reading graph theory. Here can use Narasing Dio is the Narasing Dio for Indian authors book, and John Auden Bondi and U.S. Murthy is one of the famous graph theory model, and Harari, Douglas, and this is also one of the famous graph theory book, and Harari is also one of the famous book for graph theory. And also we have the graph theory and an application, Jonathan Grass, and by graph theory and its application, John Eller, and we can have graph theory and its application. These are two books for reading for graph theory and its applications. Okay, graph, what is already cases we can have the mathematical formulation for this graph model. Always graphs have this two vertex. These are two set. One is a vertex set, another one is edge set. We can formulate a graph based on this two set. The vertex set need not be edge set may be empty, but vertex set need not be empty. Therefore, we can have model. Here, wages can be represented by this always by represented by the set node set, that is E1, E2, etc. En, and vertices is equal to V1, V2, etc. Vn. This is the mathematical model, mathematical formulation of a graph model. Here, I am having 5 vertices and seven edges. Here we have the edges E5 and E4. Therefore, this EV from V1 to V1, we have the two edges. This edges is known as parallel edges. And here V2 to here one loop have V2 to V2. Therefore, this is a graph of graph of loop. Okay. Here we can have the vertices. And graph model we can represent in terms of V1, V2. We can have flexo such a group represent friendship graphs. This graph is also the friendship graphs. Here model we can have how which one is friend. Flexo and Blender have the friend, and Blender and I have friendship. Neela and Am have the friendship. But Bender and Francis have no relation. Therefore, there is no age between this one. Therefore, this is the friendship graph. Then we can model the names as the nodes as a names, and the relation between these two friends is represented as a age. Here, the same relation friendship graph can be modeled into another structure. This one. Okay. This previous graph has looked like this strip structure. This same relation we can have the another structure. Can you see? Okay, this nodes are same and relation are same, but here the structure is different. Okay, the structure is different. The relation between the friendship is same, but the structure is different. Okay, from these two graphs, what you will observe here, we can represent their graphs in many ways, infinite number of ways we can represent a given graph. The structure of graph will be vary without altering the relation. Okay, graph means we can have the binary relation between the two objects. This two objects is given, I named as a two nodes. Okay, here before we have to observe that one graph may be drawn infinite in many ways and always provide the same information. Therefore, a graph is a structure of describing the relation between these two objects. Already I told what is a self-loop and parallel edges. Here I am going to take on five types of graphs. First we are going to see simple graph, multi-graph, and pseudo graph, and directed graph, and directed and multi-graph. There are two graph models. One is based on directed, and another one is undirected model. The directed model research is same analogous to undirected models. Some of the definitions only vary. Here, what is we are going to see simple graph. The simple graph has is a what does mean? Simple graph means most of the structure can they take only simple graph. That is simple graph without loop and parallel edges. Therefore, here in this graph, this first graph is a not simple graph. It has a parallel edges and loop. Second one is a simple graph. Most of the properties and problems derived for simple graphs. Here multiple graphs is a graph is having the multiple of parallel edges without looping. Here multiple graph means having the parallel edges between the two nodes, but it has a except here the loop. Here this is a multiple graph. We can see the cities distance between the cities San Francisco, Los Angeles, and we have the route between the cities San Francisco, Los Angeles, Denver, Chicago, and Detroit, Washington, and New York. This is how Denver and Chicago we have the two paths from Denver and Chicago and Detroit, and we have the multiple paths. Therefore, in multi-graph means it have parallel edges without having the loop. And this simple model is a directed graph to model a network and rooted problem. We can use the simple graphs. The pseudo graph is a multi-graph, but it is not have a loop. Therefore, this one is a pseudo graph. It is a loop. Each graph has each edge has a loop. Okay. Here San Francisco has a loop. Here parallel edges also there. Pseudo graph means parallel edges also graph have, and also each node have the loop. Each node have the loop. Therefore, this model is a graph model is a pseudograph. Here San Francisco, Los Angeles, and Chicago, all of them have self node, self loop, and also we have the parallel edges. Okay, parallel edges and all the vertices have the self loop. Therefore, this is the graph is a pseudograph. Someone may have assigned the next. Suppose here in previous graph, I am dealing only assigning not assigning the here this in this graph I am not assigning the values to the edges and vertices. Suppose you are willing to assign how much the relation between the two objects, we can have the assign weight to the graph edges of the two nodes. Here I am waiting this one. Weight function is represented by W from the edges from to R. Here R is a set of real numbers. We can assign the weight between these two nodes by the real numbers. Here I am taking one examples here, and here 3 to 6. Here I am taking only directed graphs from 1 to 4. Here 3 to 5 have assigning the weight 1.5. Some applications we need to assign how much it is related between two objects. Therefore, we have to give weight for this weight function. Therefore, it is important for without giving the weight function. Therefore, it is useful for many applications for using weight function between the two vertices. And this is basic definitions. Here finite graph and infinite graph. Mostly we have to use finite graph. The number of vertices are finite, and it means this is an example for infinite graph. Second graph is an infinite graph. Here this is the instant and degrees of the concept is very important. We have to be dealing many concept in applications in graph theory. Is how much, how many, how the degree of the concept is here. How many edges are instant? We can make this instant means how which is based on the two analogues. One is instant based on the vertices and instant based on the edges. Also similarly we can have adjacent based on vertices and adjacent based on edges. Here also we have this one. Something I am going to take one graph. I am taking the previous graph. Okay. Now this previous graph, I am taking the instant and adjacent. Here, this San Francisco, we have the name as San Francisco, Los Angeles for the nodes of this graph. Here, the Los Angeles and Francisco is the adjacent vertex. Adjacent. Therefore, there is a relation between this one and this is adjacent. What are the adjacent vertices of San Francisco? Los Angeles, Denver is the adjacent to this one because there is an edge between this one. What is the instant? Instant means how many, what are the edges are instant. Here it's the same Weisler. Here the Los Angeles, what are the edges? The San Francisco and Denver is adjacent. Therefore, this is the instant. How many edges are instant? Here the degree concept is based on how many edges instant on this vertices. Here San Francisco, here this one. Here suppose you have here loop, therefore the degree may be counted as twice. Here the two edges are instant on this one, therefore this is of degree is 4. Here I am taking the previous graph, this one. This graph, what are those adjacent? Adjacent vertices are New York, this Toronto, Boston and Washington. These are the adjacent vertices adjacent to this New York. Therefore, what is the degree of this New York? This is a 3 edge. 3. Therefore, here how to find the degree of this concept? Here you have to have how many edges are instant on this vertices. Here, this is a concept I am hearing here. Okay, this one. Here I am taking this graph. This is an isolated graph. Isolated, we can have isolated vertex. This is a pendant vertex, and we have the series. Here, isolated vertex means there is no edges. Already I told in graph basic definition is vertex set need not be need not be empty. That edge set may be empty. Therefore, this here I am giving a V4 is isolated vertex. Here, this based on this independent vertex means we have of degree 1. Here V3 is of degree 1. Therefore, this V3 is of pendant vertex. Okay. These are the basic concept. This null graph without having. This is also graph. This is also graph, but the graph having no edges. Okay. This graph is named as a null graph. We have subgraph. What is a subgraph? Here we can have this is a whole graph, and removing the some edges, this graph, this subgraph of K5. Here I am having the graph K5, removing the some edges. It is here. This graph is also subgraph. Okay, this is a containing. Okay. A graph G is a graph is denoted by H, and the vertices of H, W is contained in V, and the vertices H's of F is contained in V. Therefore, this is the subgraph of K5. So, just you deleting the whole graph is also a subgraph. Okay, just you deleting some of the vertices. Suppose you are to deleting a vertices, there is a one concept. Suppose you deleting the vertices means we have to eliminate all the edges instant on the vectors. Suppose you are deleting an edge, simply you are to deleting the edge only without affecting the vertices. Okay, this we have to. There are two ways to produce a subgraph. You can simply deleting an edge or deleting a set of vertices or simply deleting a set of edges. Just you have to remember, you have to deleting an vertex. You have to delete all the edges instead of the vectors. And for suppose you are to deleting an edge, simply you are deleting the edge without deleting the vertices. This is a subgraph. Here there are the three subgraphs for this graph G. Here H1, H2 and H3. I have this one. Simply two vertices with one edge is also a subgraph. The whole graph may act as also a subgraph. Is normal is a subgraph is normal is based on the subset, a set and subset concept also. Here are some of the special graphs. Here already this is a graph, but what is the difference here? This first graph G is a graph. What is this graph? This graph, the graph A is attached to A, B, and D and C, but it is not have the relation between C. Okay, but it is not direct edge between A to C, but it has traveled from A to C. Okay, this is not a complete graph. This complete graph means each vertex is joined by another vertex. Okay, this is a complete graph. Even a single vertex is also a complete graph. Here, the complete graph is denoted by Kn, capital Kn. Here, the simple graph is this one is a K1. The simple vertex is also K1. This one is K2. This one is K3. I have told one complete graph means that is each vertex is connected by all of the remaining vertex by direct edge. By direct edge means exactly from H half from one vertex to all other remaining vertex. Okay, this is a K5. Because complete graph have more connection bond. Because we removing in complete graph we cannot separate the graph. Okay, we cannot disconnect this graph. Okay, okay, complete graph is more strong than other graph. Suppose your model is the complete graph model. Okay, we cannot disconnect this. We cannot decompose into different groups. Another important one concept for more natural structure is based on five-parted graph. Okay, five-parted graph is also a graph, but the structure is different. We have to partition the vertex into we can partition into two non-empty subsets. After that, and each edge having one empty and each without having each edge between two vertices. Between these two, we have no edge. Here, the simple graph is a called the vertex that can be partitioned into two non-empty subsets V1 and V2, and so that no edge in G connects either the two vertices into. Suppose you want to post represent the persons in your village by no between two village in same persons we cannot marry. Therefore, we have the vertex between V1. Okay, this graph is five-parted because each connects each each connects a vertex in the subset of males with vertex with the subset of females. We have this problem as have the five-parted graph. Here, this five-parted graph. Here, this is the here I am taking cycle. C3 is the cycle, and we have the C3 is a five-parted graph. I already told five-parted graph means we have the vertex set. This is partitioned into two non-empty set in which both ends, both vertex set need not have the edges. Okay. Here V1, V2, V3 because there is no way to partition the vertex into two sets so that there are no edges both endpoints in the same set. We cannot partition the vertex set into this one. Therefore, C3 is now the bipartite graph. Okay. Here it is about C6. But cycle means we have the starting. We have to travel starting from one point to this is a close. This one. Suppose we have to travel V1 to V1. Therefore, this is a cycle. Here C3. This is a C6. But it's a C6. Here the cycle means cycle from starting the number of edges in the cycle is known as 6. Therefore, this is a 6 number of edges in the cycle. He have to partition C6 into 5-parted graph. Can you partition? We have to partition the 6 vertices into 2 non-empty subsets. Here, what are the sets we have to classify? We can classify as this cycle as a V1, V5 and V3 is a one set and another set is V6, V2 and V4 is a another set. Okay. Okay, what is the condition here? We can partition this one here without changing the relation. Here V1 to V6. Therefore, there is an edge. V1 to V6, and also V6 to V5. What is it here? V6 to V5. V6 to V5 have an edge, and V5 to V4. V5 to V4 have an edge. V2 to V3 have an edge. Therefore, this C6 can be partitioned into this graph model. Okay. And we can combine the concept of complete and bipartite graph. We have the complete bipartite graph. Okay, this is the complete bipartite graph. In bipartite, one vertex is joined to all other remaining vertices of the another set. Okay, here upper the vertices, this three vertices is one set, and this two vertices are another set. Therefore, these three vertices are connected to below the two vertices. Okay, this is a complete bipartite graph. Complete bipartite graph can be defined as a the notation key m comma n. Here m is the number of vertices in the one set and upper set, and n is the number of vertices in the another set. Here complement is another important concept. We can use many applications. Here complement of graph. Here to just normal. Suppose you have to have the set concept. What is the complement? Suppose A has a set 1, 2, 3, 4. U has a set 1, 2, 3, 5, 6. What is the complement of E? We have the set 5 and 6. Okay, same concept. We have applied the same area for his complement of a graph. Here, how to find complement of a graph? This vertex set may be same, but edge set is different. What is the edge set? How to find the edge set? Whenever whenever U and V have an edge in the graph G, it is not there is no edge in G dash. Therefore, this is a complement of a graph we can have. Okay. Here first I'm assuming the one graph G, we can find the graph G dash. Okay. And if or only suppose U and V have no edge in G, but there is an edge in G dash. Okay. G dash is the complement of a graph. We can denote this one. Here is complement of a graph. Here suppose I have in U and V. How to find this G dash? These vertices are same. U and V have an edge in G, therefore there is a no edge in G dash. Okay, but I am having X and V. There is a no edge in G, but you have to construct G dash. How to X and V have an edge. Therefore, this is the make complement of a graph. We have edge set are same, but whenever U and V have an edge in G, there is no edge in G dash. Whenever U and V have no edge in G, there is an edge in G dash. This is the you can make complement of a graph. Here operations of graph. Operations of graph is going on most on research to combine two graphs and produce the one graph. Okay, we have to given here one new structure. Okay, new structure for this one. There are so many operators are doing operators, algebraic operators are using to combine two graphs. Combine two graphs. To produce this operations on graph can be used in to construct networks, network communications and network security to give the new produce a new structure of your problem. Okay, that prove that you can combine these two graphs and taking only two union of this graph. Union of graph means you have to join in the vertices and edges. Okay, the joining the vertices and edges. This have also two types. This also two types. We have joining this two graph. This vertex set and vertex set of G1 and vertex set of G2 operations on graphs are the vast area. There are so many research are doing on operations on graphs or articles. Here we can have this also. We have the two types analogous. Here the vertex set may be empty, vertex may be disjoint and may not be disjoint. Based on this two classification, we can operations on graphs. Also, we can have the edge set may be empty and edge set may not be empty. Based on these two concepts, we have operations on two graphs G1 and G2. Here I am taking G1 and G2. Here the same, here I am taking the red color vertices on G1 and G2 and combining G1 and G2. I have the produce one graph K5. Already I have told K5 is a complete graph with 5 vertices. Therefore, this two graphs G1 and G2 I am going to produce the K5. Here I am told for union means just you joining the vertices and also the edges. Okay. Here first graph 1, 2, 3, 4, 5 and also second graph also have four, but this the vertices are is not disjoint. Okay, not disjoint means not different. Okay, these two vertices here I am taking this vertice. This vertices, these four vertices are same. Therefore, just I am taking just joining the relation between this one. Okay, here are all the graphs. Here, this two have no edge, but in G2 have an edge. Therefore, this like this one. Therefore, from this G1 and G2, I am producing this K5. Okay, operations on graphs is very important. Next, how to representing a graphs. Okay. We can representing graphs already I told I representing the graphs by nodes and edges, but in computer area and computer science there are to producing algorithms and you have to find applications. We can represent in matrix form. Can represent the graph into matrix form. This is the important structure. Okay, there are two types of representing graphs based on the vertices, instant vertices, and adjacent matrices. Okay, two types we can have. Okay, what is here? You have to represent the graph model into matrix model. Here I am taking one, representing one is adjacency matrix, another one is this is the representing adjacency matrix. Here adjacency matrix, how to represent here between two vertices there is a between two vertices is adjacent means we have here value 1 in matrix, otherwise the value is 0. Okay, here how to represent this one. Here and having this one. Therefore, this is the binary relation. Here there is a graph. That is adjacency matrix. Here you have to find the adjacency matrix. Here the vertex A, B, C, D. Okay. Adjacency matrix is based on the vertices. Okay. Here A first row A, B, C, D. Okay. Here column also A, B, C, D. Just I am not writing this one A, B, C, D, A, B, C, D. Here A and E have no loop, therefore the value is 0. E and B have H1, therefore we have one adjacent. Therefore E and B has adjacent, therefore it is have the value 1. And E and C have an edge, therefore it is have the value 1, therefore it is a 1. Therefore in adjacency matrix have the value 1 and 0. This is a binary relations. Okay. And another way of representing graphs into matrix form, that is matrix form is another one is instant matrix. Instant matrix is based on, that is how already I told how many edges are instant for a particular vertex. Okay, this one. I am going to represent here. This is a matrix A, B, C, D. Okay. Here in column wise we can represent A, B, C, D. In column we have A, B, C, D, and in row we have the edges. We have the edges. What are the edges here? 1, 2, 3, 4, 5, and 6 edges. 6 edges. Therefore, instant matrix gives the relation between the vertices and edges. Okay. Here I have the vertices E. How many edges are instant on the vertex E? What are the edges are instant on the vertex? Here. Here 1 is instant on the vertex A, therefore we have the value 1. And 2, the edge 2 is instant on the vertex A, therefore we have the value 1. And what are the 3, 3, 4 is not instant, therefore we have the value 0. Okay. And 5 is instantaneous, therefore we have the value 1. 6 is not instantaneous, therefore we have the value 0. Therefore, this is the way to another way to representing a graph in matrix form. Okay. And we have to remember on this value, matrix value how is the number of edges here 0. It may be number of times, it is 0, 1 and 2. It may be have the value 1, 2 and 3. Suppose we have the parallel edges. Here 3. We have the values as 2 times are repeating means we have the parallel edges. Therefore, how many times it is have the value 2. Therefore, in M we have the matrix value either 0, number of times is number of times 0, 1 or 2. But in adjacency matrix, it's a symmetric matrix. In adjacency matrix, is a symmetric matrix. It is deals with the relation between the vertex and vertex. Therefore, it is a adjacency matrix is a symmetric matrix, but instant need not be symmetric. Okay, these are the two types we can represent in given graph. I gave another examples to represent this one, adjacency and instant matrix. You can go through the same graph. What is the difference between this one? Okay, adjacency matrix is a symmetric matrix, but instant matrix need not be symmetric. Okay, this one. Next one is isomorphism of graphs. This isomorphism of graphs is most of the important structure to find which of the structure is isomorphic. We have the two graphs. We have the two graphs, two structure of the graph. Which one? Which is it is isomorphic to another? We have the definitions. Under the definitions here, isomorphism H is we have the two vertices. Two graphs have the same number of vertices and same number of edges, and also the same number of there is instant. I am taking here one instant relation is also preserved. Therefore, these three conditions are satisfied with graphs are isomorphic. Here I am taking this one. These two graphs. Okay, these two graphs G1 and G2. These two graphs have same number of vertices. There I am marking first graph A, B, C, D, E. This is the first graph. Second one is 1, 2, 3, 4, 5. Therefore, this is for 5 vertices. Therefore, the vertices are same. First condition is satisfied. Second one is number of edges. Number of edges is also same. But here another one is we want to check the instant relation. The relation is preserved between these two edges. Now you are to mapping this first graph vertices here, and we are mapping first vertex A to 2. Here I am making here A to 2 and B to 1 and C to 5, D to 4 and E to 3. Okay. Based on this mapping, I am going to check this relation is preserved for the graph. Then if it is a the relation is preserved means the graph is isomorphic. Relation is preserved means it is a isomorphic. Here I am taking here A, here A to E. Here A to E has an edge. Therefore, we have to check the A to E. Here A is mapped to 2. and E is mapped to 3. Therefore, we have 2 and 3 in G2. 2 and 3 have an edge. We have to check. Here also 2 and 3 have an edge. Therefore, the instant relation is preserved. We have to check for all the vertices. Then it is satisfied for all the vertices for instant relation. Then it is a isomorphism or graphs. Suppose I am taking another one. A, suppose I am taking C and B. Okay, C and B have the edge in G1. What is C? What is C here? 5 and B. What is the B? Is 1. Therefore 5 1 1. Therefore here you have to in 5 between 5 1 1 we have a edge in G2. Therefore this relation is also preserved. Here we have to concentrate on to find isomorphism of 3 points you have to remember. First one is number of vertices and number of edges, and the instant relation is also preserved between these two edges, two graphs. Okay. Here, these two graphs are isomorphic. Yes, these two graphs are isomorphic because H I am going to have the relation. Okay, the mapping. What is the mapping here? I am taking. We have the different mapping for different that these two graphs. I am taking first mapping mapped to W is mapped to C, X is mapped to B, Y is mapped to D, and Z is mapped to A. And taking the another mapping, we have this. We can this is also possible. W is equal to A and X is tends to D and Y is mapped to B and Z is mapped to C. Both the mapping F1 and F2. These two graphs are isomorphic. Okay. Number of vertices same, edges same. This function is also the function. This instant relation is also preserved. So I am going to check only one. W here. W and X. W and X having an edge between in G. What about in H? H means here W is mapped to C and X mapped to B. Okay, up to C to B. C to B means here also have an edge. Therefore, this is a instant relation is preserved. You have to check all this point at all the edges. And similarly, we can have F2. The mapping in this mapping is also we have this two graphs are isomorphic. Okay. Here I am taking another one. These two graphs. These two graphs is not isomorphic. Here why? We can have the degree. We can have the degree. Okay. What is the here degree? Vertex degree T. Okay. Already I told. We can have. I have told one is vertices and edges, and instant relation is also preserved. The instant relation may be taken as a degree of the vertex. Here I am taking number of vertices are same, number of edges are same, but here in two graphs, in first graph the degree of the vertex is 3 for the vertex in 3, but in the second graph the degree of the vertex is 1 because only one edge is instant on D. Therefore, this is not a isomorphism. Therefore, these two graphs are not isomorphic. Okay. Next one is connectivity concept. Connectivity concept is most important in many of the applications. Here, in finding the row network. Okay, from how to connect from one point to another point, how it is connected, it is strongly connected or weakly connected. This is important to find the city network problems. Okay, connectivity is important. Here we have the two types of connectivities and edge connectivity and vertex connectivity. Okay, in a city to say in a city to city road network, if one city can be reached from another city, problems in determining whether a message can be sent to two computer using the intermediate links efficiently, planning routes for data delivery in the internet. Therefore, based these are the problems we can have the connectivity areas. Okay. Here in connectivity, we have the three concepts. One is walk, and another one is path, and another one is circuit. Walk is a alternating sequence of vertices and edges. It may be closed or open walk. From closed walk means we can travel from starting point to starting point and ending point are same. This walk is known as closed. Starting and ending point are distinct. It is the walk is known as open path. Similarly, we can have the path. Path means the vertices are not distinct. Vertices are distinct. Vertices in a walk, the you can find a path. Therefore, the vertices are distinct. Therefore, it is a path. Circuit means we can have this path is closed. This circuit is the path is closed means the path is known as circuit. Okay. Here in this graph, we have the sequence. We can travel from one vertex to V1 to V4. I'm going to travel V1 to V4. This is the connectivity. We can travel from V1 to V4 based on this edges. There are so many paths available, so many walks available. We can travel from V1 to V4. There is a direct edge. We can travel from V1 to V4. Otherwise, we can travel from V1 to V4 by using V2. Suppose I am traveling V1, E1, V2, E2, and V4. I am taking this one. V1, E1, V2, V2, V4. This one. I am traveling this one. Otherwise, we can traveling V1, E4, V3, V3, V4. This one. Okay. There are so many paths are available to travel from V1 to V4. In this, we can find from shortest path which one is maximum connected, strongly connected, weakly connected. Okay. There are already told. Suppose you want to find a path. In this path, a vertex not repeated, then the path is it is a path. Okay. Here trial means we can have no edge repeated. Okay, edge we can have a walk in which no edge is repeated. Then the walk is known as trial. Okay, walk is it may be edges are edges and vertices are maybe repeated. In walk we have the closed means starting ending same. It is not distinct means it is a open walk. Okay, this walk path and circuits are have many applications. Already I have told one mention previous slide. I have the C3. I am using the concept C3. Okay, pipe-ordered graph. I am taking the pipe. The C3 is pipe-ordered, and I am taking this one. C6 is pipe-ordered, but C3 is not pipe-ordered. I have told here. This is a proper definitions for cycle. A cycle is a closed walk. Already is a walk. Walk means it is a sequence of alternating edges and edges. Vertices. A cycle is a closed walk. Okay, in which neither a vertex nor edge appear is more than once. Okay, cycle in which vertex and edges not appear more than once. Therefore, this is a cycle, and we have number of cycles. The cycles n must be greater or equal to 3. Because for n is equal n is equal to 1 means it is simply vertex, it is not a cycle, and n is equal to 2 means it is simply an edge. Therefore, we cannot make a cycle. Therefore, n must be greater or equal to 3. Therefore, a cycle means edges and vertices are not repeated. Already I told connected graph and disconnected graph and components. In many of the applications we can suppose we have to split a given graph into more than one graphs. More than one graphs. The graph may be connected and it may be disconnected. Okay, here I am taking this one. I am taking this one. Yes, first graph. First graph is connected. First graph is connected because we can travel from one vertex to another vertex by using the any of the edges. But the second graph, go through the second graph, we cannot travel from V to V because there is a no edge, there is a no direct edge. Otherwise, there is no edge. There is no path between V and E. Okay. Therefore, second graph is disconnected graph. There's also this one. The third graph is connected, but the last graph is not connected. Okay. Here the components. Okay. Suppose you are to removing an edge. Suppose I am doing this one. I am removing any vertex from a given graph. The graph can be disconnected, and this graph is known as components. Okay. Here. These are the three components. These are the three components. Okay, the Suppose I am deleting a vertex, the graph can be disconnected, and the number of graphs in the disconnected graph is known as components. These are the connected components. Suppose I am deleting an edge from the third graph. Suppose I am deleting an edge from the third graph. What will you have? I am already told deleting an edge means just you deleting simply an edge. Therefore, what is it here? A, B, C, and D, and simply you have the E is the isolated vertex. Therefore, this two are components of the graph. Okay. Here, this already Euler is the important person to have the introduce the graph theory. Therefore, here Euler graph is based on the edges, and Hamiltonian forms is based on the vertices and circuit. This is in most of the applications I told in the after the slide. What are the applications of Hamiltonian forms and Hamiltonian circuit? Here. Suppose we have to plan for a trip, we don't need to travel all the edges more than once. That time you have to meet this Euler path and Hamiltonian graph, Euler path and Hamiltonian cycles. Okay. Here Euler path means the path that uses every edge of graph exactly once, and Euler circuit means this cycle which is a Euler path. The path uses every edge of graph exactly once. An Euler circuit means it is cycle which is an Euler path. And Hamiltonian path in a graph G is a path which visits every vertex in G exactly once. And the Hamiltonian circuit or Hamiltonian cycle is a cycle which visits every vertex exactly once except for the first vertex. Okay. Here I am suppose. This is a which of the following can be drawn paper without lifting the pencil. Suppose you have to draw a graph without lifting your hand movements, then the graph is Eulerian graph. Okay. Here we can trace which of this. We have two graphs. Which one is we can trace without lifting your pen? Okay, this one. The left graph is a Euler graph, but not as the right. Okay. Without lifting your pencil, we can draw the graph. Then the graph is Euler graph. Suppose we can move lifting the hand means the graph is not a Euler. First you have to starting the graph. I am taking one, starting here and ending here. This one and this one. Okay. Here, this is the example for Hamiltonian path and Hamiltonian cycles. Hamiltonian is based on vertex. We can travel all the vertex without repeating a vertex. Okay, this is we cannot find. This is a not Hamiltonian graph. This is the Hamiltonian cycle. We can find. We can start from the vertex, blue vertex. We can travel all the vertices and ending to this one. This graph have a Hamiltonian cycle. And also another important concept on graph models are trees. In trees, it is an acyclic graph. Okay. In graph, we have cycle, but in tree structure, in normal in tree, therefore it is a acyclic graph. Acyclic graph is known as tree. Okay. There are in data structure we can define in this data DNA and RNA data structure. We can have this tree based model. Okay, here in distance concept in trees and grass is very important to find the shortest path between the similarity between the two vectors in distance. Here a distance between two vertices can be defined d of u comma v is the least length of the path. I have already told from one vertex to another vertex we have so many paths. From this we can find smallest distance path, smallest length of the path, therefore which is known as distances. If two vertices u and v have no path, then the distance is indicated as a infinity. Here in graph, diameter and eccentricity and center of the graph. Center of the graph is most important to structuring clustering analysis. In clustering analysis, we have how the data are similar, which group are similar, which group are not similar. Okay, based on this distance concept, center of the graph, we can have clustering the data. Okay, this concept, diameter and eccentricity, center, we have to use in clustering the analysis. I am taking this one. Already, diameter is the upper bound of the distance, and eccentricity from upper bound of distance between every pair, and eccentricity is the maximum of the diameter, and center of the graph is the variance of the minimum of the eccentricity. Okay, here I am giving this one. From this graph, we can have the distance. Here, what is the distance between F and C? The C is not mentioning this one, this red color, this is C. We have to have F and C, have the distance between F and C. What are the small, there are so many paths available, what is the smallest path? Okay, we have to travel from F and C, this F, B, C, this is C. I am not mentioning the vertex node as A, please note that this is C, F, E and C. Therefore, there are two paths from F, B, C. Another way you want to go F, A, G, D, D and E. This is the longest path. Therefore, what are the smallest path from this one length is, this is F and G. Therefore, the distance between F and C is equal to 2. Similarly, you can have distance between G and C. G and C. Okay. G and C means this one. What is the here smallest one? 1, 2 and 3. Okay, here we can have G, E and C. This is 2. Therefore, the distance between G and C is 2. From this, we can find the grouping the elements based on the distance. Okay. Also, here spanning trees and is an important concept in structuring the data. Here spanning trees, it is already have the subtrees. Okay, so, what is a subgraph? Spanning tree is a tree. It is a looks like a tree in which it has the vertices are same but edges are not contained. Okay, here in red in green color, this graph is known as spanning tree. Okay. Spanning tree means it is a tree. It have the same number of vertices of the original graph, but edges are containing. It's not strictly equal, but it is containing the original graph. Okay, this is a spanning tree, but number of vertices are same. This one is a spanning tree. We can find the for this given tree we can find 9 possible spanning trees. Okay, here 9 possible spanning trees are this one T1, E1, E3, E4 and E5. So this one is a spanning trees. Okay, E2. What is E2? E2 is between V1 to V3 and E3 and E4 and E5. Therefore, this is a spanning tree. It contains all the vertices. Okay, how to construct spanning tree for a given tree? First, you have to have all the vertices. After that, you have the edges containing. Therefore, we can from this graph we can have 9 possible spanning trees. Another important one is based on already I told two directions on graph theory going on. One is undirected and another one is directed. Same definitions are applicable for directed and indirected. Only one point is this direction. We have the direction. Okay, each edge have direction ordered pair of vertices. In this directed graph also we have loop and multiple arc and concept, instant concept, degree concept, and also representing a directed graph. Always same for the directed graph. Here this is the directed graph models. Already I told here we have the two types of degrees. Here in directed undirected graph only 1 degree. Here we have the 2 degrees, in degree and out degree of this concept. Okay. Here what is the in degree means, that is thus the arrow mark here A to B. Here what are the in degree? How many edges are this instant emerging out, emerging in. Okay, emerging out means here A2 is how 2 edges are emerging out from A. Okay, therefore this is the out degree. One edge is emerging to A. Therefore, this is here the arrow mark. Here this one, this is the in degree. Therefore, the degree of in degree of A is 1, in the out degree of A is 2. Okay, this one. This is the slight difference from undirected graph, in degree and out degree. We have the direction from A to B. From this also we can have adjacency matrix and instant matrix. Okay. It is defined as like directed, undirected matrix. This is adjacency weighted. In also we have weighted graph in adjacency, undirected graph. This is we can define path and cycle. Directed graph and so complete graph. Complete graphs. Now I am going to have. There are so many applications of graph theory. This structure, the map structure, we can have a Google graph. Our Facebook is also connected for. Here's the graph model. In chemistry also we can have the graph model. Here, this in which degree of the vertex can be used to how the molecules are connected between them. Therefore, this is a graph model of this one. Okay, chemical graph theory is one of the important to define structure of the chemical phenomena of model. Okay, this is the famous Keller structures. Okay, this Keller structure can model into perfect matching. Model into perfect matching. This perfect matching yellow bonds are Keller structure. And we can have the shortest graph, building the shortest graph. We can have a set of points, we can find the shortest collection the edges. Okay, what are the here? Shortest path between this, so there are so many algorithms available to find shortest path between the two nodes. Okay, here we can find this concept, we can have the road and railway network connections, telephone and internet cables. We have to construct class pipes for the shortest path, connection in electronic networks and neurons connecting bits of your brain, how much it is shortestly connected. Because these are the shortest tree and shortest graphs have to use in this applications. Suppose you want to have 4 terminals that we should to connect which one is the we have to use the shortest path. Okay, we can have 4 terms, we can connect which one is the shortest. Therefore, we can have this type of models. We can connect this 4-way. Okay, this 3-way. We can have this one. And social networking, we can have friendship like your Facebook, how your friends, one friend to another friend, how it is multiplied. This one. Therefore, it is a street structure. One node and another one is your friend and another your friend. We can have it is a tree like this, spanning tree. Now we can have already I have 5-parted graph. five-parted graph, we suppose one job, suppose you want to jobs, company jobs and employees. This concept can be modeled in five-parted graph, and each employee is situated for some staff, and assume that each persons perform at most one job at a time. Okay. The problem is how to job be assigned so that maximum number of jobs can be performed simultaneously. Suppose this graph is modeled as a five-parted graph. In physics, we can have this circuit analysis. Okay, the circuit is represented as a graph with elements as edges and nodes as a nodes. This graph, this switching circuit can be modeled as this one. Okay, here is the graph of the circuit. We can study after this circuit. We can have the network. This circuit. 1, 2, 3, 4 and 5, this one. And connecting between this 1 and 2, we have the edge between 1 and 2. Okay, this is a model to connect in network circuit. And telephone wire, modeling a telephone wire between the houses, how to have the shortest, this one, how to connect this one. Okay. This is more, suppose you are to connecting this one, this is more expensive, therefore this one. We have the more directly given direct edge, okay, direct edge from one central office to all other this one, therefore it is more expensive, therefore we have to model this structure as a this one, okay, this one, minimize the total length of wire connecting the customer, therefore to minimizing the total length. This is a shortest point. This, how to minimizing this one, we have to find the minimum spanning tree. Minimum cost spanning tree problem, we can use this this concept. Suppose you have to supply set of houses, electric power, water, sewage line and telephone line. To keep the cost down, you should connect this house with your spanning tree concept. Already I told spanning tree is a tree in which the vertices are same but the edges are reduced. However, the houses are not all equal distance apart. Therefore, to reduce the cost even further, you would connect the houses with your minimum cost spanning tree concepts. Similarly, we can apply this spanning tree concept as a data graph. We have to minimize the minimum cost spanning tree. Is a spanning tree that has a lowest cost. We have to construct from one more. We have to construct from A to D. We have to find which one is the shortest weight of this one. There are so many algorithms are available to find minimum cost of this spanning tree. In mazes, already we have to some of them are known mazes. Here the cells are vertices and the open doors between the cells are edges. Okay, this we can have from one starting to another one without repeating this one. Since there is exactly one path between any pair of cells and any cells can be used as a start and finish. Therefore, describes this maze as described as a spanning tree. Okay, in a tree we have only one path between any two nodes. But in a graph, it is so there are so many paths between one to another node. But in a suppose you take a tree, there is only one path between this one. Therefore, this maze we can represent as a spanning tree. We can travel. We can start from any one of this maze. From I am giving an arrow mark, and you have to travel. You have to travel all this one. We can come across the travel out by exactly one path. Therefore, the maze likes a spanning tree. This one. Okay, and having here this one, I having the line from starting to how to end. While not every maze is a spanning tree, most can be represented as such. The nodes are places within the nodes. Okay, there is exactly one cycle-free path from any node to another node. Okay, all mazes are this particular maze is a spanning tree, but all mazes may not be spanning tree. Therefore, only one path is available from one one in spanning tree from one node to another node. Planar graph is also another important graph. You have to restructure the graph. Okay. Here, planar graph means I have already told one graph. Here we can draw the edges intersect only at the planes. Okay, without intersecting edges, we can draw a graph without intersecting an edge. The edge, it is intersecting only at the vertices, but not intersecting in the edges. Okay, but here I am taking this one. Suppose we have three houses and three utilities. Is it possible to connect each utility to each of these three houses without any line crossing? Okay, this is a planar graph. You have to draw. You have to face this model this problem as a planar or non-planar. So without any lines crossing. Okay, here planar or non-planar. This is also here. Now, what are the houses? Suppose we have three houses and three utilities. Okay, what are the utilities? We have housing H1, H2, and H3, U1 and U2 and U3. You connect all these three utilities, this H1 without intersecting the edges. Therefore, solution. Okay, this one is plan. This one is planar. Okay, this K4 we can travel this one. K4 already I told. We can have this edge between this vertex to this vertex. Therefore, this suppose we have an edge from this to this one. Therefore, it intersecting an edge. Therefore, we can redraw the graph like this. We can redraw the edge like this. Therefore, it makes no edges are intersect. Therefore, K4 is also planar. Okay. In planar, first you have to make the not crossing any lines. Okay. Similarly, K5 is not planar. Therefore, we cannot draw the graph without intersecting the edges. Therefore, K5 is not planar. Okay. Planar graphs. And also kind graph chess models. In chess model, we can have the Knight graph. This is also important applications. We can start from one place to this in the Hamiltonian cycle. Hamiltonian cycle is used to form the chess model. Okay, a cycle that uses each graph vertex of a graph exactly once is called the Hamiltonian cycle. This Hamiltonian cycle can be used in the Knight graph. Okay, in the chessboard. Okay. Here, each square in the chessboard can be represented as a node in the graph, and each legal move from by the knight can be represented as a edge in the graph. This model, chess model, can be represented as a graph model. In legal move, is to sit one square along one square and two square along the two other, two strip. For n by n knight to have the total number of vertices is simply n into m. How many total number of vertices for n2 is the number of vertices n square, the number of edges. We have the edges n into n. How many edges are there? 4 into n minus 2 into n minus 1 edges are there. Okay. In Knight graph can be modeled as a pipe-parted graph. Pipe-parted graph in this one. This is pipe-parted graph. Graph also pipe-parted graph. Already I told pipe-parted graph means we can partition the graph into two non-empty subsets. This pipe-parted graph can be colored as two color. Already after that I am going to color. Coloring is also another important graph to classify the data. Here, this pipe-parted graph have always two colors. I am doing this one, chromatic number. Here coloring, how to color a given graph without repeating the, without adjacent vertices have the same color. Okay, this is the chromatic number. Chromatic number is represented by psi of g. Here, this is the graph. What is the chromatic number of 3? Here, I am going to coloring a given graph in which the adjacent vertices cannot assign the same color. Okay, for that I am going to chromatic number. How many colors we needed to color the given graph. Here I am giving for this particular graph I am having 3 colors to need to color the given graph. Here I am going this one. First vertex I am giving the color blue, green and red and blue. Here adjacent vertices receive different colors. Therefore, this is the chromatic number of this graph is 3. For this one, I am going to find this one. Always the chromatic number of the cycle is 3 if n is odd or 2 if n is even. Every tree or 2 more vertices are, every tree or more vertices is 2 chromatic. Every tree is 2 chromatic. Why? Every tree chromatic, 2 chromatic, because the tree is have a unique path between any 2 vertices. Therefore, we can assign there are different vertices are in the path. Therefore, we can assign 2 colors is enough to color the given graph. Therefore, the tree is a 2 chromatic. One of the famous problem is 4 colors is proposed by Francis. We can have the regions, only 4 colors is enough to color the given regions as a distinct to adjacent vertices receive the different colors. This is an example of 4 coloring. We can have the regions, we can use 4 colors differently. Here each region is represented by the vertices. Here I model this one. 4 colors must be needed to color the given graph. Here this is suppose I am going to take 3 colors. 3 colors are not enough to color the given regions. Therefore, we need 4 colors to region the given graph. Here I am giving this 4 colors: yellow, blue, and this one 2 blues. Therefore, I need 4 colors. Suppose I am taking yellow, some other colors. Therefore, the vertices are adjacent. Therefore, it is not satisfying our coloring property. Therefore, we need 4 colors to color the given regions. Okay. Here we can map the coloring to the given map. Therefore, what the maps here, the nodes are represent this one. The regions are represented as a regions. Okay. Adjacent edges, adjacent regions need not have the same colors. Okay. Here. Therefore, we need 4 colors to color this regions. Here we have to have minimum, how to minimize, how to minimum number of colors useful for this. Coloring can be used for scheduling concepts. Okay. For timetabling problems, suppose you have the problems x1, x2, etc. Excel, and subjects y1, y2, etc. y1. In which adjacent have not received the same colors. Okay, this one. Okay, and how this timetabling problem, I modeled this one as a graph model. Okay, and now I am coloring the given graph. Okay, for mapping also this one. For scheduling applications, we can have the coloring concepts. Is graph coloring. Another one is the important one. It's a dominating set. Dominating concept can be used in locating many applications, location problems, utilities, and we can use a dominating. Here we have the minimal dominating and domination number. Minimum polynomiality of this is known as domination number. Okay. Already I told in distance cellular architecture, we can use this based on distance. We can use based on distance. We can color the graph the same colors. Okay. Minimum distance between two cells using the change handles for satisfying single to noise ratio. Here I am using this 3 is the pattern. Here I am having the same distance. How the colors? We have the 3 colors. Already I have told students, dominating set can be used in chess borders. This one. Here dominating set means we can dominating set of every node G is either in it or adjacent to it. Here In many network applications, we can have the how it is dominating. Therefore, we have to concentrate on this red colors instead of other colors dominating. So, therefore, this is dominating three. You have to so in applying this concept in network. Just you have to concentrate on this red color node without this one. Therefore, here 1, 6, 8, 9, and this 1, 6, 8, and 9 dominating all the vertices in the graph. Therefore, this is the dominating set. Here, this is a cube can be model in this dominating set. Here, our motivation is how to find the minimum domination number. This is the minimum how to minimize the domination number. Suppose we have to thousands networks or thousands nodes are there. You have to concentrate on only 10 nodes because the 10 nodes are dominating all other nodes. Therefore, you have to concentrate on this 10 node means it is easiest for our work. Therefore, here our motivation is to find the minimum domination number. There are many algorithms are available to find the minimum domination number. For in many in biological also we have the dominating which one is dominating suppose predicting the cancer in this one which cell is dominating other this one we can find this which one is minimum dominating this one this is the we can use it is we can find many applications. Also, we can apply probability and also graph theory we can have. This is a random graph called Erode, and we have random graphs 1959 on random graph list to authors. Here this internet graph and we have the random graphs in nature. This is collaborative graph. We can assigning the broadcasting frequencies. We can transmit the geographical regions and assign broadcasting frequencies. Some part of transmitters require different frequencies to avoid interference. Problem is to minimize the number of different frequencies that are assigned. You can have this one. Network design, image processing, and data mining and website designings. These are the graphs we can have. For network design, connectivity, transversing, adjacency matrix, and covering algorithms. And I'm not cover here this one. There are two types of cover: edge cover and vertex cover. This covering algorithms are used in network design. And for image processing, there is a spanning tree and edge connectivity and regions Euler regions are there. Euler formula is there. Phases, number of regions, relation between phases and regions. It is this concept are used in image processing and data mining. Subgraphs and isomorphism are used in data mining. Okay, these are the applications. And also nowadays we can have spectral graph theory. There are rooming in one spectral graphs. This we can apply the linear algebra and graph theory. We can have spectral graph theory. Now I am going to stop here. There are the research areas in graph theory. We have to find graph similarities, graph graph coloring, Latin square graph, domination in graphs, and also decomposition of graphs, algebraic graph theory, line graphs is also now one of the emerging research, and spectral graph theory and microscopic graph theory. These are the emerging research areas in graph theory. I am going to stop here. These are my references. Okay, thank you. I am stopping here.
Thank you, ma'am. Really, your lecture was very interesting and informative one. I am very sure that the participant would have enjoyed and enriched their knowledge in the domain of graph theory. Thank you, ma'am. We will go ahead and take some time for questions now. Just a reminder, please be sure to type your questions into the chat box. We have some questions, ma'am. Shall I
Okay.
ask the questions
Okay.
one by one, ma'am?
Okay.
Okay. First question, ma'am.
Hmm.
Whether construction of a graph vertices and edges are essential or in other way can be designed.
Yeah, essentially can represent as a matrix form. It is essential.
Okay, ma'am. Second question, ma'am. What are the applications of graph theory?
Here, applications we can have communication network and in biological networks we can use this concepts in applications of graph theory. To
Okay,
construct
ma'am.
protein, DNA and RNA structure for our human beings, in this model we have graph structures. To
Okay,
find
ma'am.
similarity of proteins RNA, we can have graph similarity concept we can use.
Okay, ma'am. Next question, ma'am. Whether degrees of freedom have any relationship with graph construction?
Degrees of freedom. I
Have,
don't know what is the degrees of freedom. Degrees is that I don't know this question answer. I don't know. What is I know? I know. I don't know whether degrees of freedom. I don't know
okay, ma'am.
what he accept.
Okay, ma'am. Okay, ma'am. Last question, ma'am. Example for rural trail and Euler tour, ma'am.
Example for
Rural trail and Euler tour.
here Euler tour is based on edges. We have the tour without repeating an edges. That is, edges are repeated only exactly once. Uh, from starting to ending point are same. Trial means starting ending point are not same, but edges may not be repeated. So the difference.
Okay, ma'am. Ma'am, one question here. What are the applications of graph coloring for
Graph
research
coloring
purpose?
or graph coloring we can have to construct the network and also to clustering purpose we can have the graph coloring concept to separate the regions, to grouping the regions. For grouping the regions we can have the graph coloring concepts.
Okay, ma'am. Thank you, ma'am. We have covered all of our questions, ma'am. Thank you,
Okay,
ma'am.
thank you.
Next, I call upon Mr. R. Madhivanan, Assistant Professor, to propose his vote of thanks.
Okay, good afternoon, everyone. We are at the end of the today's webinar. It's my immense pleasure to thank you all at this occasion. It's my privilege to thank our Honorable Chairman, Dr. K.S. Rangasamy, MGF, and our energetic Vice Chairman, Mr. R. Srinivasan and Ms. Kavita Srinivasan, Executive Directors, who always guide us in all our dates. I also extend my sincere gratitude to our respected principal, Dr. V. Radhakrishnan, for his valuable support. I extended my wholehearted thanks for our dynamic resource person, Dr. G. Tamizhendhi ma'am, for accepting our invitation and for her thought-provoking ideas. And my special thanks to our convener, Ms. M. Sujata ma'am, Head PG Department of Mathematics. Also, I extended my heartfelt thanks to all participants. I would like to thank Mr. E. Rajendra Kumar, Head UG Department of Mathematics, and Mr. B. Harikrishnan, Assistant Professor of Department of BCA, for his technical support to conduct the webinar in smooth manner. Last but not least, I would like to thank the coordinators and my colleagues for the backbone of this successful webinar. Again, I thank you all.
Thank you, sir. Thanks again for joining us today, and we will see you the next time.